probably haven't done. What we're talking about today are these things called piecewise functions. And what piecewise functions are don't draw this, they're literally pieces of functions. If you look at this graph, notice how it's increasing at a steady rate. It hits a certain value of x, and then it increases at a different rate. See how it changes like that? So what happens is, if you look into the graph itself, you'll notice that you could probably figure out what the slope of the line on the left is, can't you? What is it? 1, okay? Is it a positive or negative slope? It's positive. It's got a slope of 1, and what would its y-intercept be? At 0, okay? So the equation of that first line, pretty easy to decipher. The equation of this first line, I would say, would be y equals x. You okay with that? Now, where does that equation change? After it passes 0. So this equation this equation occurs from 0 on the domain to the left, correct? So what you think is that equation is increasing, we would say, from negative infinity to 0. And then at 0, it changes. At 0, it changes to a different slope. We could probably figure that out then, can't we? Up 2 over 1, up 2 over 1, up 2 over 1. So what do you think the slope is? 2. So then at 0, it changes to y equals 2x for when x is greater than 0, and this is for when x is less than 0. The idea here is that it is what we call a domain restricted graph. It changes. The function itself changes. This is very, very common. You probably have seen this in your normal lives. For example, if you go to the movie theater, children from a certain age to 12 are one price. From 12 to senior citizen is another price. From senior citizen to however old you are is another price. It's restricted on the domain. Your age determines your price. Okay? If you go to, what was that? I think there was a place where you can eat your weight, or your weight costs how much your food's going to be. It's all dependent upon that. The domain values you substitute in generate what you pay for. Car insurance. I brought this up with the 12th hour, I think. Did I bring it to you guys? Oh, I forget. But the idea that certain age groups pay more in insurance because it's restricted within that range value, and then it changes over time. That's kind of what a piecewise function is. Also, what piecewise functions could look like this. That's called a step function. And that's kind of what it gets at as far, if you think about costs of movie tickets. From 0 to 2 years old, you pay $1. When you're 2 years old to 4 years old, you pay $3. That's the idea. Obviously, I'm just making up numbers as I'm going here, but what a piecewise function does is that it is a restricted via the domain, the x values, to figure out what your y values are, your range. Does that make sense? So, like I said, this might be something new, but in essence, it's fairly simple. In fact, I guarantee you've probably done this. Remember the game Plinko? Real, or not Real Fortune. Price is Right. They drop it, the ball, and you go, bing, I won $1 million. That was Plinko. You were putting in a value, and it would find its way down to the end. So, what we have here is, well, first of all, do you know what that stands for? F of x, function of x. You're right. Very good. F of x stands for function of x. It's synonymous with y equals. Okay? They kind of mean the same thing. And what happens here is you have probably done some very simplistic function notations before. For example, you probably did this. What is f of 7? When you see f of 7, notice that there's some restriction here, isn't there? Which of those two equations would you substitute 7 in for? Would you substitute it into the top equation or the bottom equation? Why? Correct. Everybody see that? That's what we call by a domain-restricted function. The domain, those values of x, it's telling you what function you'll be working with. So if I say, hey, what's f of 7? That means I go to my Plinko machine, and I substitute here, 2 times 7 plus 1, and I would get 15. You probably did that when you first learned about direct substitution with function notation. I'm guessing that's very common with an Algebra 1 class, right? Thank you for at least making me feel good for a second. I know that I've seen that before. Also, what if I had f of 2? Top or bottom? Bottom, because it's equal. Right? So I know that f of 2, and so on. The idea here is that you could have multiple functions, but dependent upon what value your input goes, you have to decide which output you're going to get. That's where piecewise comes in. Piecewise is that. It's that domain-restricted version of a function. Okay? Now, when it comes to graphing these, when you graph them, excuse me, when you graph them, how you set up and do it, it does not change, but you'll probably want to have an eraser. Okay? And I'll show you why I would say that. So, take 2 sheets and pass them around. Please, thank you. I forgot to hold those sheets. Sorry. I got hold on to mine. If you want a whole bunch, I can pass that around. I don't know if you guys have binders and whatnot. I have a hand myself. You don't want extra? Sure. You can use your own graph paper if you want. Better to have more than not enough. That's fine. Thank you. You guys got spares too? Oh, I'm sorry. So here's what I do when I'm dealing with these piecewise functions via graphs. Graphing either one of these is really simple, isn't it? X plus 2 or 2x plus 1. That's really simple. Not much going on there. But what I want to do, though, is look at where you have a domain restriction. When I say domain restriction, I want you to look at your if x is less than 2, if x is greater or equal to 2. That's the realm of my domain restrictions, which means something funky is going to happen around when x equals 2. So normally what I'll do is I'll put a lightly drawn line in to remind myself that something weird's going to happen around 2. If you can. Okay? Let me shut this off and see it better. Or not. There, I'll just do this. I know something weird's going to happen around 2. So what I'm going to do is graph both of those lines on the one grid. X plus 2. What's your y-intercept? What's your slope? 1. So I start at 2, slope of 1, I go all the way up, and I go all the way down. This is the time when I do piecewise functions that I like to fill my graph, bless you, going in both directions. Now I'm going to go and look at my restriction. This graph should only be graphed for when values of x are less than 2. So I go to my line of need to pay attention to something. I want all my x values to be smaller than 2, which means my graph should be coming this way. But what should I do to that 2 right there? Should it be a solid dot or an open dot? It should be an open dot. Very good. The reason that should be then an open dot is because this is a less than. So what I can do, what I normally would do is this. I'm just going to circle it, make it just like overly exaggerated, because you're on the right spot. And you've already made a dot there, but if you over circle it, I know that it's an open dot. Does that make sense? Everything to the right I no longer need. So that's why I was saying it's not a bad idea to have an eraser. And believe me, after you do a few of these, you probably won't have to go on both sides of the graph because you'll recognize there's the domain restriction area, and I only have to go to the left of it for this part, and then I have to go to the right of it for the other part. You might not need to erase it all. But I find that the first couple times you do it, it's not a bad idea. Okay? And now I just connect all the dots moving to the left. Okay? And now I do the same thing for the other graph. No, it is not. This is not, this is just connect the line. It's just looking at, the only part that I have to worry about open or solid or is the domain here. This is still just a functional, it's a linear equation. Okay. Excuse me. I do the exact same thing with the other graph. The other one is 2x plus 1, which means I start where? At 1. Switch colors here. Start at 1. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I know that this graph has to move to the right, so there's no reason for me to graph anything else to the left, because the domain tells me that it's for all values of x such that they're greater than or equal to 2. So I can get rid of these first couple of dots that I had, except for this one. So these first few dots that I put on there, where I started at 1, went up 2 over 1, up 2 over 1, I can not worry about those, but I still have that first dot when it hit 2. And that's a solid dot there at 2 because it's greater than or equal to 2. And I'm moving for values of x that are greater than that. So I just continue this graph going this way. So when in this function, when you hit the number 2 for x, it jumps from one graph to the next. It's the idea of, if you go back to the idea of a movie theater ticket. Kids are certain you're $7 until you're 12 years old, and then when you're 12 years old, all of a sudden you're $12. That's the idea. Okay? You have different price points for different age brackets. Even though this is new-ish, it's not that tough-ish, is it? You just have to pay attention to where your restriction occurs. Should I do more? Yeah. All right, try this. You'll get really good at drawing Jay Leno's face.
Yeah, I got these cars and things. Blah, 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 blah. I should wear a denim shirt. Blah, blah, blah.
Who's Jay Leno?
Yeah.
Okay. Jay Leno was the guy that did the Tonight Show before Jimmy Fallon. He's a comedian. He took over after Johnny Carson.
Johnny Carson was the guy that had the Tonight Show before Jimmy Fallon, before Jay Leno. He was probably one of the original late night talk show hosts. I'm sure there was, and I forgot their name. It's a little before my time. There was somebody before Carson. There was black and white TVs as well, but you only got 4 channels on, in case you guys knew that. Back in my day. We have 2 graphs, 2x minus 1 and 3x plus 1.
Where's the domain restriction occurring? Around 1. So again, I would start this by putting a lightly drawn vertical line at x equals 1. That way I can pay attention to what occurs around there. Okay. And then I start graphing. 2x minus 1. What's your y-intercept? -1, and your slope is? And right away, I hit my domain restriction. So I'm going to stop on this one and not continue on. I'm going to reread what the domain restriction is for that first part of the function. Now, is this first part of the function going to occur to the right or to the left of your phone of that domain restriction? To the left. So do I need to continue moving that way? Nope. So I'm just going to turn around and just go down 2 left 1, down 2 left 1, because I know that's what it's going to have to do. Okay. Everybody okay with that? Because I know that my restriction happens here, so I'm just going to stop, reread it, and go. This is what I meant by sometimes you can fill it up and go back and reread, or just go to it and then just finish out. So down to 1. And I know it's moving this way. I left that as a solid dot because it said so. Now the next one starts where? At 1, what's your slope? 3. Change color. So start at 1, 1, 2, 3, over 1. Back to my domain restriction. Should this be an open or a closed dot on the domain restriction? Open. And obviously, we've already talked about, I don't need to go to the left on this because it's got to go to the correct. And now we just go up 3 over 1. And I just connect my dots. Yes, because that's what it'll look like. Unless it's a completely jump in continuity, which is, you will see what that looks like in terms of the domain. It's fairly simple. Okay? Because sometimes we could have, let's say if x is greater than 1, but, I'm sorry, x is greater than 1, but it's less than, less than 4. So I could just make it stop at 4 and just have that small little segment. If I wanted to. But it's really simple as you're looking through it. Did everybody hear what she was asking? Okay. What she was asking was, will it always just kind of just continue on through? Well, sometimes you could have just a specific smaller range of just a segment. Here we're drawing arrays. You can have segment stuff, plateaus, segments. You can have all these different things. It's just a matter of, excuse me, reading what the domain says. And remember, the domain is just your values of x. Okay, remember, what comes first in the alphabet, x or y? And what's first in the alphabet? Domain or range. What's first in the alphabet, horizontal or vertical? Well, there's a reason why I keep asking that. And I'm so glad you asked that, because look what's that. Okay? It's not you. No, it's not. It's not. Try it. See what you can do. Okay? Try it. See what you can do.
for example, if I'm looking at 2x plus 1, I'm not going to worry about my domain quite yet. I'm just going to go ahead and just graph the whole thing on the entire 10 by 10 grid. And I start, let's see, we start at 1, up 2 over 1, down to left 1, and now I'm going to go ahead and look at the restriction zone of that. This one has to be between -2 and positive 6. Does it say less than or equal to, greater than or equal to, or anything? So I'm going to look at my domain value of -2. This becomes an open dot. It's got to go to the right of it, so I'm going to go ahead and just erase those. It's okay. And then I have to go to 6. Well, it's up there. It happens. It happens. And there's that graph. Okay. Graph the other one. -x. What's your y-intercept? 0. Very good. What's your slope? Excellent. 0. This way. Up to there. That graph only occurs where? In between -8 and -4. So between -4, 5, 6, 7, 8, and -8, I'm just looking at that part. The rest of it gets erased. Don't know what kind of a real-world application has a graph that looks like that, but I do know that it's domain restricted and it works. Again, all you're doing with these is you're graphing them like you would any other graph, and then you go back and erase where it does not occur according to the restriction within the domain. Right? No. All right. Piecewise not terrible, is it? Now, let's talk about the other one that's in this section. It's called the step function. What do steps look like? Like this? Or like this? Or like this? So they're just basically steps. Okay? When you have what's called a step function, let's see if I've got the next one. Nope. When you have what's called a step function, normally you want your steps to be what to the ground? Very good, because if they're not parallel to the ground, what happens? You're slanting, it's kind of tough. If they're wet, you're going to fall over, you're going to die. But if they're parallel to the ground, it's just like walking up and down the stairs, right? Now, when you get into it, you start really thinking about it. Each step is generally, practical terms, they're usually the same space apart, aren't they? They have to be. No, it's nice that they are, because you wouldn't have to just take steps and all of a sudden go. You know, for us with longer legs, it's not a big deal. But if you don't have longer legs, you're kind of like, you know.
bad. But that's the idea. Not that math is bad, but anyway. When you have a function that equals, when you have f of x equaling 1, remember, that's the same idea as saying y equals 1. What kind of line is y equals 1? It's horizontal. And what number does it go through? 1. When you have f of x equals 2, what does it go through? F of x equals 3, and so on and so on. So when we get to start looking at the graph of this one is restricted where? So we have f of x is equal to 1, including 0, not including 1. So what would I put at 0? A solid dot, a closed dot, very good. And what would I put at 1? An open dot. So I have a closed dot, open dot. What do I do between the two? Connect them. And then I go, that fulfilled that first step, if you will. What do I do next? I go up a step. My next step is at 2. And it's restricted between 1 and 2. And then I go to the next one. It's at 3 between 2 and 3. And then at 4 between 3 and 4. That, ladies and gentlemen, is a step function. Boom, 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 boom. When you are 1 year old, you pay $1. When you are 2 years old, you pay $2. When you're 3 years old, you pay $3. That's kind of what that means. Right? That's kind of what that looks like. What are the other ones? Like kids' meals. Kids 5 and under are free. Woo! We couldn't do that very long with my kids, especially Moose. Moose is Moose. So Connor, we got away with have eaten off the kids' meal for free stuff for maybe a little bit longer than he should have. But then again, he was smart. But I'm 6. Save me $7. But Moose. No, our kid's name is Moose. No, seriously. We named him Moose when my wife had him. The doctors were like, "Oh my god, oh my god!" We're like, "What's wrong? What's wrong?" And they're like, "He's huge." The kid he was massive baby, like 10.5 pounds, 22 inches. His shoulders were as big as his head. So he was this. Yeah. So he's been Moose his whole life, and we've just said, "Yep, that's Moose." So we called him. His name's Moose, and he's still a bigger guy, but he's really tall for a first grader now, and he's just outruns everybody. And Lord knows you bump into him, he's just knocking you over. It's funny. He plays soccer, so he's really good, and he's naturally just become a defender. So I don't know if you guys play soccer a lot. He's turned into a natural defender where he's out there. He got knocked over one time last year. He got up so fast, went over, and he slide kicked and blocked the goal. My wife and you guys know Mr. Vincent down over at Rosette. He and my wife coach the soccer team. We're all living in the same neighborhood. Our kids go to the same schools and stuff. And he was out there coaching when Moose, we got to call him Ryan at school. But when he did that, like, oh my God, I got it. It's real close. He's a beast. But anyway, so Moose, he was free for a while, and then all of a sudden he had to start paying for more food because he just got old. Don't know where this story got me, but. Do you do another one of those? No. I think so. Wait, let me back up here. There's one other thing I wanted to show you really quick. Do you think you could write the equation of that?
Yeah. Do you think you can write the equation of that? Okay. A lot of times when we look at writing equations of piecewise functions, we start at the left and work our way to the right. So the first equation that we come across is usually the one we put on top, and the second one is, and so on and so on and so on. So just looking at this, usually you're not going to get anything that's going to be super crazy, nutty that you're not going to be able to tell, is that an x squared? You know, we try to be pretty lenient, pretty straightforward as far as the linear equations are for this. What's the slope of that first part? -2. Very good. What did it go through? 2. It's gonna be rather evident what it's going through and what the slopes are. So everybody agree that the equation of that first line is -2x plus 2. The other one, you might have to work backwards to figure out your y-intercept. But it's not bad, is it? You can kind of just look at it and say, well, it's going up by 1, so it's got to go down 1, left 1, which makes your y-intercept what? -3. What's your slope? 1. So the other one would be x minus 3. Where did the domain switch? At 1. So the domain switched at 1, so the graph on the left is for when x is less than or equal to, greater than or equal to. Less than or equal to 1. And then on the right, it's x is pretty simple, isn't it? Okay. I gave you guys 2 sheets of graph paper. One of them was to help you with some note stuff. The other one was so that you can do some homework. The homework I've already posted on the Confuser net. And if I'm not mistaken, it is, I forgot what page, it's like something, but it's numbers 21 through 30. Those are the graphs. And then 35 through 40 are writing the equations. Okay. I think there is one equation that you have to write that's, bless you, that's like a plateau. They come up and it flattens out. So you'll have 3 parts to it. And when it's in the middle, it's sometimes hard to distinguish whether or not it's an open or a closed dot. So what I would do, when it gets to the plateaus like this, it's not tough. You're just counting slopes and stuff. Here, I would just put the plateau portion being closed dots, the increasing and decreasing portions as open dots. Okay. I'll show you what I mean by that tomorrow. The one thing I would say on 38, what's your scale going by? Going by 2. So that's the other thing it's got to be careful of. Okay. Other than that, you guys should be flying right through it. I'm not going to worry about this whole idea of this greatest integer function on the calculator. There's no reason that we don't even know what button it is on your calculator to do that. So, all right.